Okay, welcome to day 4, linearization. We're going to look to see how we can use equations of lines to approximate values. So back in the day, they used this technique called linearization to approximate values. They said they knew some point x sub 0, y sub 0, and they knew some curve, and like it's too hard to figure out this next y value. So they decided to find this one, because this one's easier because this function is curvy, this function is just a line. So they said the slope of this line is equal to the derivative at this x value, and it's very easy to figure out what this next value is. And even though it's not the same, they are very close. So even though L1 is called the L sub x is called the linearization, it's not the same as the function itself, but they are close. So they say it's approximately equal to each other. And that's what they worked on. They just said, you know what, we can't figure it out. Years ago, that there's no way they would spend the time to figure out 5.1 raised to the 6th power. It's just take too long, and they didn't have calculators. So they figured out a way to do it by writing a linear equation. This is the best way to write a linear equation, and the only thing I really need to figure out is the slope, and that's just taking the derivative of something, which we've been working on for the last month. So what three things do I need to write a linear equation? Well, first thing I need is some x value, given x value. I need a y value, and I need a slope. The x value will be given to you. The y value, it could be given to you, but sometimes I could determine it by plugging it into the function, and that gives me the y value. And when I want the slope of the tangent line. So what do? I take the derivative and plug in the x value that it was given to me. And then I have specific numbers for all three of these guys. I can plug them into my equation. Let me write this down. So now that I have all three things here, I can rewrite my linear equation like that. And sometimes we don't put it called x sub 1. We call it this equation, and this is what I'm going to use, where it approximates the value that I'm looking for. But it has to be close. Whatever the new x value must be close to the original x value. Otherwise, the farther away from the original x, the worse approximation it is. So let's go back to this graph above, because it's asking, according to the above graph, is this linearization an overestimate or underestimate, and why? Well, if I look at this graph, I could definitely tell that the linearization point is less than the actual function point. It is below it. Well, why is it below it? It is below it because the function is concave up. Whenever you have a concave up graph, the linearization will always be below it. So go back to our notes. Is an underestimate because the function is concave up. And conversely, if I had a graph that was concave down, my linearization would always be above the curve. So in this case, L of x is an overestimate Because any point I'm trying to find on this curve, the linearization point would be above it, because the function is concave down. So let's try an example. So we're trying to find 4.1 cubed without using a calculator. So my original x I'm going to use is 4. I'm plugging it into this function, so f of 4 is going to be 4 cubed, which is equal to 64. So my linearization is right now m x minus 4 plus 64. I need to know the m. How do I find the m? Well, the m is the slope, which is just the derivative, so I do f prime of x is 3x squared. That's an easy one. I plug in 4. I get 3 times 4 squared, so f prime of 4 is equal to 48. And my new equation that I want to use is 48x minus 4 plus 64. Again, I'm trying to find it for 4.1, so I'm going to use x equals 4.1. L of 4.1 is equal to 48. 4.1 minus 4 plus 64 equals 48 times 0.1 plus 64, which is 4.8 plus 64. So my linearization of 4.1, or my approximate value for 4.1 to the third power, is 68.8. Well, let's compare it to the actual value of 4.1 cubed. So if I do 4.1 cubed, you could go to your calculators. I plugged it in, and I realize there is an actual value of 4.1 cubed. Now, is this an overestimate or underestimate? Well, obvious reasons, L of 4.1 is an underestimate. I can see that 68.8 is less than 68.921. That's obvious. But the real reason why, if you look on this graph, right here at 4, there's a point on the graph, and if you look on this curve, because the x cubed graph is concave up at x equals 4. That's why this is an underestimate. Okay, don't give me this 68.8 is less than 68.921. I understand that. That's true. I want a calculus reason why. We're trying to use calculus reasons why we justify things. Okay, another example. Again, we have this x value of 4.1, and we have a different function, f of x equals the square root of x. So I'm going to use my x of 0 is equal to 4 again, and I plug this in here. I get the square root of 4, which is 2. So right, my linearization is m x minus 4 plus 2. I need to know what my m is. That is my derivative. So f of x is equal to x to the 1/2. Its derivative is 1/2 x to the negative 1/2. And when I plug in 4, I get 1/2 times 4 to the negative 1/2, which is 1/2 times, well, the square root of 4 is 2, so the negative square root of it is 1/2. So f prime of 4 is equal to 1/4. And my linearization is 1/4 x minus 4 plus 2. And I go ahead and plug in, use x equals 4.1 because that's really the original. That's the the value for x I wanted to use. So my linearization of 4.1 is 1/4 4.1 minus 4 plus 2, which is 0.25 times 0.1 plus 2, which is 0.025 plus 2. So my linearization of 4.1 is 2.025, or I have approximated the square root of 4.1 as 2.025. Okay, let's go to my calculator And if I actually do the square root of 4.1, my calculator has it to, let's say, 4 decimal places is 2.0248. I think that's pretty darn close. So let's think about, is this an overestimate or underestimate? So obviously L of x is an overestimate. That I can tell just by saying 2.025 is bigger than 2.0248. Not by much, but it is. But what I really want to hear is because f of x equal the square root of x is concave down at x equals 4. And you come over here, here's x equals 4. You can see at this point right there that it is concave down. So I'm going to show that these functions, 1 plus x raised to the 15th, e to the x, are approximately equal to these other values when I have something very close to x equals 0. So again, I'm going to plug in 0. So f of 0 is equal to 1 plus 0 to the 15th, which is just 1. So my linearization is going to be n x minus 0, which seems silly, plus 1. So now I have to figure out the slope. So I have to do some chain rule here. So my function is equal to 1 plus x to the 15th. If I recall, that prime, by using my chain rule, is going to be 15, 1 plus x to the 14th. The derivative of x is just 1. So when I plug in 0, I get 15 of 1 plus 0 to the 14th. And I get 15 times 1, which is 15. So my linearization is going to be 15 x minus 0 plus 1. But we all know x minus 0 is just x. So my linearization is 15x plus 1, or better yet, 1 plus 15x. So I have shown that 1 plus x to the 15th is about equal to 1 plus 15x. When I use something very close to 0. Let's try an example. Let's try x equals 0.01. So if I plug it in this part, 1 plus 15 times 0.01, I get 1.15. If I do 1 plus 0.01 raised to the 15, I put in my calculator, I get 1.16. Pretty darn close. How about e to the x? Well, f of 0 of e to the x is e to the 0, which is 1. So my linearization right now is m x minus 0 plus 1. My function is e to the x. Its derivative is e to the x. I plug in 0 because that's my given x. I get e to the 0, I get 1. So this is my slope. So my linearization is 1 times x minus 0 plus 1. And if I want to be careful, I could say my linearization is x plus 1. Or I have shown that e to the x is about equal to 1 plus x. Let's try something small. Let's try x equals 0.1. Well, 1 plus 0.1 is equal to 1.1. And now let me do e to the 0.1. I put that in the calculator. I get 1.105. And again, I can see they are very close to each other. So I'm going to plug in 0, so f of 0 is ln of 1 plus 0, which is ln of 1, which is equal to 0. So I have my linearization is m x minus 0 plus 0. And then I have to do my derivative. So if my function is ln of 1 plus x, its derivative is going to be 1 over 1 plus x. The derivative of x is just 1. So I plug in 0. I get 1 over 1, which is just 1. That's my slope. So my linearization is 1, x minus 0 plus 0. But if I clean it up, I just get x. And I have shown that ln of 1 plus x is equal to x. Let's try something small. Let's try x equals 0.1. Well, obviously, if I plug it in for x, I get 0.1. If I do ln of 1.1, I get about 0.0953. Not too bad. Maybe not as good as the other ones, but pretty darn close. And finally, this last one. Let me plug in 0 into this function. I get 1 over 1 plus 0, which is equal to 1. So my linearization is m x minus 0 plus 1. Let me take this derivative of 1 over 1 plus x. Well, this is really 1 plus x to the negative 1, and its derivative is going to be negative 2. Excuse me. Negative 1, 1 plus x to the negative 2 times the derivative of x is just 1. So the derivative is really negative 1 over 1 plus x squared. Plug in 0. I get negative 1 over 1 plus 0 squared, which is negative 1 over 1, which is negative 1. That's my slope. So my linearization is negative 1, x minus 0 plus 1. I don't need the minus 0. So I get negative x plus 1. And I have shown that 1 over 1 plus x is about equal to 1 minus x if I rewrite it in a different order. And let me try something small. Let me try x equals 0.1. So if I do 1 minus 0.1, I get 0.9. And if I do 1 over 1 plus 0.1, which is 1 over 1.1, that is equal to 0.90909 repeating. Pretty darn close.